Good morning, dear students. In this session, we are going to discuss about glasses and liquid crystals. The contents of this session includes glasses in that properties, types of glasses, uses of glasses, liquid crystals, different liquid crystal phases, and defects in liquid crystals. Let us start with glass. What is a glass? It is nothing but a supercooled liquid having no definite melting point and I- and a high viscosity that prevents crystallization. Glass is a uniform material of arguable phase produced when the viscous molten material cools rapidly below its glass transition temperature without sufficient time for a regular crystal lattice to form. Coming to the properties of glasses. This glass is a amorphous in nature and it is a brittle. Brittle means, of course, this is an hard, but it is a breakable, and it is a transparent as well as translucent, and it is a good electrical insulator, and it is unaffected by air, water, acid, or chemical reagent except HF, that is hydrogen fluoride. No definite crystal structure for this glass, and it can absorb and transmit and reflect a light. What are the raw materials used in the manufacture of glasses? Here, the most important fundamental constituent of glass is a silicon dioxide. Next one is sodium oxide, which is obtained from sodium carbonate, that is a soda, which lowers the glass transition temperature. The soda makes the glass water soluble, which is usually undesirable. And another material, that is a raw material, is lime, that is a calcium oxide. Usually it is obtained from the limestone, that is calcium carbonate. Another material is magnesium oxide and aluminum oxide, and these two provide better chemical durability. So the resulting glass contains about 70 to 74% silica biweight and is called a soda lime glass. Coming to the types of glasses, these are classified based on other ingredients which change its properties. First one is soda lime silica glass or soda glass, or this can also be called as soft or window glass. The raw materials which are used in the preparation of this soda glass is silicon dioxide, that is silica, SiO2, sodium oxide, calcium oxide, magnesia, and alumina, that is Al2O3. This glass has a high thermal expansion and poor resistance to heat. It has poor resistance to the heat, and it is used for making food or beverage containers, and it is used for windows, some low temperature incandescent light bulbs. There also this soda glass is used, and lamp envelope and tablewares. This soda glass is used. Next one is borosilicate glass or pyrex glass. The raw materials are silica, boron trioxide here. We are using soda, that is Na2O, and alumina. And this glass starts heat expansion much better than the previous one, that is a soda glass or a window glass. And this glass is used for chemical glasswares, cooking glass, car head lamps, etc. And these are commonly used for making reagent bottles, that is laboratory purposes we are using, and industrial equipment, exterior lighting, laboratory wares, optical components, and household cookware. Lead oxide glass or crystal glass or lead glass. Here also we are using silica, lead oxide from red lead, and potassium oxide, which is obtained from potassium carbonate, soda from sodium carbonate, zinc oxide, and alumina. These are the raw materials which are used for the manufacture of lead glass. Because of its high density, it has a high refractive index, high dispersion power, it has high electrical resistance, and it has high homogeneity and does not undergo de-vitrification and cut off harmful UV radiation. This glass cut off the harmful UV radiation, and this glass is used for making lenses, neon sign tubings, and cathode ray tubes, optical instruments. In the optical instruments also we are using this lead glasses and spectral prisms. And the next type is safety glasses. It is obtained by placing between two layers of glass, that is a transparent butyryl plastic with a suitable adhesive, and cementing them by heat and pressure. Usually this glass is used in automobile windshields. You can see the picture here, shields and goggles, safety goggles. Coming to the next heading, that is a liquid crystals. What are liquid crystals? What are the properties of liquid crystals? See, these liquid crystals are nothing but a crystals, that is matter in a state that has properties between those of conventional liquid and those of solid crystals. Properties between liquid and solid crystal. And these may flow like a liquid, but its molecules may be oriented in a crystal like way. This is what one important point. Flow like a liquid, of course, but its molecules may be oriented in a crystal like manner. There are many different types of liquid crystal phases which can be distinguished by different phases. Liquid crystal, is it a solid or liquid? Question is arises. See, we know that latent heat of transition. What is this latent heat of transition? The amount of energy required to cause the phase transition is called as latent heat of transition. And what happened in the liquid crystals? The smallness latent heat of liquid crystal to liquid phase transition is evidence that liquid crystals are more similar to liquids than that of solids. Let us see three phases, that is solid phase, liquid phase, and gas phases. Let us discuss these three phases. See, in solid phases, what happened? Molecules with both orientation and positional orders. Molecules are there with both orientation and positional orders and are held to each other strongly in solid phases. What happened in liquid phases? The molecules in liquid phases, no orientation and positional orders. They doesn't show orientation and positional orders, but are held together by weak intermolecular forces. happened in the last case, that is gas phases, right? So here there is no ordering or no intermolecular attraction here. Here let us see the orientational order. Before that, liquid crystals differ from liquid that there are still some orientational order possessed by the molecules. You can observe in the picture how they are arranged: solids, liquids, and the orientation of a liquid crystals. As the temperature increases, how the molecules are arranged in liquid crystal as well as liquids. What is orientational order? Assuming that, let us see the picture here. The direction of preferred orientation in liquid crystal, okay, is this direction, okay, is this direction, and it can be represented by an arrow called the director of the liquid crystals. That arrow represents the director of the liquid crystal. Coming to the different liquid crystal phases, we have so many phases. First one is nematics crystal phases. Here there is no translational orders. Nematic means, it's a Greek word. It means thread-like structures. Nematic means thread-like structure, and there is no long range translational order in this nematics crystal phases, and it is the least ordered mesophases. Coming to the smectic, it is one dimensional translational order. It is again a Greek word. It means soapy like structure. Here we can see the smectic A to K phases. In smectic A phase, molecules, you can observe this picture. What happened in the smectic A phase, molecules tend to be perpendicular to the smectic layers in smectic A phase. What happened in the smectic C? Here the molecules in the layers are parallel and tilted. Slight tiltation is there here, right, with respect to the normal of the layers by a tilt angle. Some tilting is there, right, in smectic C type. And coming to the next phase, that is a chiral liquid crystal or cholesteric. This is also known as a chiral nematic. Here in this case, molecules have non-symmetrical carbon atoms. Here non-symmetrical carbon atoms, and thus lose mirror symmetry. And these crystal phases show a helical structure. You can observe here helical structures, and the director rotates about a horizontal axis. You can see the second picture here. The distance for one full rotation is called as pitch. And the next phase is pleiotropic liquid crystals. These are two component systems where an amphiphile is dissolved in a solvent. Thus, pleiotropic mesophases are concentration and solvent dependent. The amphiphilic compounds are characterized by two distinct moieties, that is a hydrophilic polar head and a hydrophobic tail. You can see the picture here so that you can understand the hydrophilic as well as the hydrophobic tail. Examples for this kind of crystals are soaps. Next one is thermotrophic liquid crystals. These are nothing but a solid changes to liquid crystalline phase above the melting point. If transition between the phases are given by temperature, they are called thermotropic. What is thermotropic? Means transition between the phases are given by the temperature. This structural requirement leads to two general classes. One is calamatic and another one is discotic liquid crystals. See, what are these calamatic and discotic liquid crystals? See, calamatic liquid crystals, compounds that possess an elongated shape here, in this case, are responsible for the form anisotropy. Isotropy means having same structural in all the angles. Here anisotropy means not same properties when we measured. Okay, so discotic liquid crystals, these are disc shaped molecules are the basic building blocks. Here in discotic liquid crystals, disc shaped molecules are the basic building blocks, and the order can be in the terms of an orientation or in the form of columns. You can observe the picture here. The order is in the form of a column. Defects in liquid crystals. The abrupt changes in the brightness seen in the picture signal here, you can see here, a rapid change in the director orientation in the vicinity of a line or a point singularity known as disclination. A disclination is a region. What is this disclination means? It's a region where the director is undefined here. The following is a diagram that shows the orientation of the director around a disclination. See here, a normal unlined sample of a nematic liquid crystal doesn't usually have a director. You can see the picture here, three pictures. In this sample, direction in all the regions of the sample. The director changes throughout the sample and at positions where the director abruptly changes directions. No specific director can be defined and a defect is generated. These defects can be studied by polarized microscope by interaction with the polarized light. Since liquid crystals are anisotropic, they cause light polarized along the director to propagate at a different velocity than that polarized perpendicular to the director. The polarization of light is rotated by the liquid crystal molecules. If the polarized light incident on the liquid crystal, you can observe here liquid crystal, if the polarized light incident on the liquid crystal has its polarization direction either parallel or perpendicular to the director, it will appear black and under crashed polarizers. You can observe here. When viewed under a microscope with sample between two crashed polarizers, the director usually points in different directions at different points within the sample. The specific texture observed under microscope give the information about the type of liquid crystal phase formed. So coming to the revision of this session, we have discussed about classes. In that properties of classes, types of classes we have discussed, and uses of these different types of classes also discussed, and we have discussed about liquid crystals in that different liquid crystal phases, and also we have discussed about defects in liquid crystals. These are some of the references I have referred. Thank you.